In this video, we will be talking about undamped free systems, which is the simplest vibrational system. There are three examples of undamped free systems here in this picture. We have a spring mass system on the left, a torsional system in the middle, and a simple pendulum, as you see, which is on your right-hand side. All these systems are governed by a very simple equation, which is of the form mx double dot is equal to minus kx. That is, the second derivative is proportional to the function itself, which is the equation of motion of these systems. And from these equations of motion, we would like to obtain solutions given the initial conditions. Since this system is free, there is no forcing, but given the initial conditions, we would like to find solutions for those initial conditions. That is, if you have a pendulum, you just pull it a little bit and you let it oscillate. What kind of oscillation it does? That's what we want to find out. Another system, which is the same system actually, is a mass that is hanging, as you see, from a wall with a spring. It has a spring that is unstretched, but when you hang it from the wall, it comes to an equilibrium. We want to find oscillations about that equilibrium. And the equation of motion is still mx double dot plus kx is equal to 0, the same equation as we see. The gravity, effect of gravity, can be cancelled if you measure the equations from the equilibrium. The same system again, but I show you how to derive the equations. We just use the Newton's laws. The only force acting on the system is the spring force, and the spring force here is equal to the inertia force, and therefore mx double dot is equal to minus kx. These are the initial conditions. The initial displacement is x0. If there is an initial velocity, there might be an initially velocity given. We call it v0, and we want to find the response of our system. We have an initial displacement and an initial velocity. These are the initial conditions. So what is the solution to this? This is our equation of motion, a second order differential equation, which can be written as follows. The second derivative is proportional to negative of the function itself. Actually, there are two functions which satisfy this. It is the sine function and the cosine function. And the total solution is simply the addition of those two functions. So the total solution for your system is C1 sine omega nt plus C2 cosine omega nt. Now here, there is an interesting thing. Omega n we define as root k over m. It comes from this k over m here. It is the frequency of oscillations of the system. And we call it the natural frequency because it is the frequency of free oscillations. When you let a system oscillate by itself with no external forcing, the system will oscillate at its natural frequency. And the natural unit for that is the radians per second. That is, it is the circular natural frequency. Okay, now we see that there are C1 and C2 terms here. These are constants and they depend on the initial conditions actually. And we need to find them using the initial conditions. And as I said, the initial conditions are x of 0 is x0, x dot of 0 is v0. So what do? We take our solution and substitute x of 0, zero value of time. When you substitute it for x of 0, this term drops because it's 0. This term becomes a 1. So C2 becomes x0. C2, we have found it, it's x0. Whereas for x dot of 0, we have to take the derivative of this equation. So omega n comes to the front, and sine becomes a cosine, cosine becomes a minus sine, from which we saw that the C1 term, which is this term, is V0 over omega n. Okay, so the total solution for our equation in terms of the initial conditions is given here, x0 cosine omega nt plus V0 over omega n sine omega nt is our solution. There is another possible solution for the same equation, which is equivalent as we have shown in the harmonic motion case. We can, instead of writing sines and cosines as in the previous slide, as here, we can write the solution as a single sine function with a phase shift. In this case, our unknowns are not C1 and C2 as before, but now the unknowns are x and phi. And they can be found from the initial conditions also. We just have to substitute the initial conditions to this equation to find x and phi values. Here, I have given you a picture of simple harmonic motion, which we discussed before. Again, you have the amplitude, which is our capital X here. The period is 2 pi over omega n, etc. We will come to that later. Okay. Now, I repeat the same picture here. We see that the omega n is the natural frequency. Period is the time taken from one oscillation, one peak of one oscillation to peak of another oscillation, kind of. That is measured in the period, whereas that is called the period and measured in seconds. The frequency in hertz, that is cycles per second, is 1 over the period. It's very simple. But in terms of natural frequency, it is omega n over 2 pi. Now, in technical units, we usually use hertz, but for calculations, we need to use radians per seconds because it's necessary for the trigonometric functions. So if we want to find the amplitude and phase from the initial conditions for this description, as you remember, x equals sine omega nt plus phi, x0 is, we substitute t equals 0 here for the time. So x0 becomes x sine phi, v0 becomes, we take the derivative, omega n x cosine phi. So using these, we can solve for x and v0. How do we do that? We just divide the first term to the second one. So you have x0, excuse me. X0 equals x sine phi, v0 equals omega n x cosine phi. So let's see, x0 equals x sine phi, and v0 equals x cosine phi times omega n. So we divide these into each other, and the x terms cancel, as you see. Sine phi over cosine phi is tangent phi, equals, therefore, omega n x0 over v0. So phi is simply the inverse tangent of this term. And in order to find the x term, actually, what we do is we take squares of these things. So we take, for example, x sine phi squared. What is that? Plus, let's say x squared cosine squared phi, which becomes, as you know, x squared will be equal to x0 squared plus, what will that be? V0 over omega n squared, from which x is equal to square root of this. X0 squared plus V0 over omega n squared. Or if you take omega n out, this is the expression you get. This expression is what you will be obtaining. So that is the solution for the form for the amplitude with amplitude and phase. So the solution is simply, as you see, an amplitude and a phase function. Amplitude and phase, as we see, period is 2 pi over omega n, and the normal frequency is 1 over the period, or omega n over 2 pi. Okay, the last thing is we have the velocity and acceleration terms. The acceleration, velocity and acceleration are simply the derivatives of the position. Since we have found the position, we can find velocity and acceleration. That's no problem. We just have to take the derivative of it. Velocity is the derivative of position. So it is when if you have a sine function with a phase shift, you get a cosine function. But cosine function is simply a sine function with a phase shift of pi over 2, as you see. And also, the acceleration is the second derivative. So it is the derivative of the first derivative. So you get omega n squared plus sine now, sine phi. But this minus sign can be replaced by a phase shift of pi or 180 degrees. As you see, displacement, velocity, and acceleration are quite related, and the amplitudes of velocity and acceleration are related as well. For example, if xm is the amplitude of the position, let me see, xm is the amplitude of the position, xm times omega n is the amplitude of the velocity, and xm times omega n squared is the amplitude of acceleration. Okay, so much for undamped system. We will continue with damped systems.